Hello everybody, and welcome to the first of 4 DYNAMO presentations in our series hosted by the Climate Variability and Predictability Program of NOAA's Climate Program Office. These webinars are intended to showcase research funded by the Climate Variability and Predictability Program that was conducted as part of the DYNAMO Field Campaign, which ran from the fall of 2011 to the spring of 2012 in the Indian Ocean. This field campaign, consisting of in-situ observations from moorings, aircraft, land, and shipboard sensors, is part of a larger research program involving data analysis, modeling, and forecast improvement components that are ongoing today. The overarching goal of DYNAMO is to develop a better understanding of the MJO because it is an important influence on the global climate system, especially on a seasonal to interannual scale. Advances in our understanding of the MJO can improve prediction skill in climate and weather models, allowing them to provide better forecasts and projections in the future. In pursuit of this goal, DYNAMO tried to capture the structure and evolution of cloud populations, air-sea interactions, and larger-scale environmental interactions related to the MJO. This series of presentations will share the latest results from these projects and will allow the PIs to discuss the importance of their work, outcomes, and lessons learned to date with a broader scientific community. We will start this series with a presentation by Agustin Vincilios, an assistant research scientist at the University of Maryland's Earth System Science Interdisciplinary Center. He will be discussing real-time monitoring and forecast support for DYNAMO.
In the outline of my talk, I will, as it is the first in this series, I will try to remind you the importance of forecasting and the interface between the weather and climate, and then provide a very brief presentation of the DYNAMO campaign before discussing the monitoring and forecast support that University of Maryland and NCEP provided to DYNAMO. Then I will be focusing on forecast challenges that we faced during DYNAMO by confronting atmospheric model forecast to DYNAMO observations, comparing coupled and uncoupled forecasts at seasonal time scales, and if I have the time, confronting the oceanic model forecast to DYNAMO observations. So what is tropical subseasonal variability? Is oscillations, so it's variability with periodicities between week 2, 3, and 4. And its importance is not only the importance of forecasting this subseasonal variability is not only for its own sake, as we know that it affects directly breaks in monsoons and things like that have a direct impact on society, but also because, and as mentioned many times in the literature, it modulates the probability of formation of tropical cyclone or extreme precipitation events in the western conus. And I will come back to the tropical cyclones at the end of my talk. On the other side of the spectrum, on climate forecasting, subseasonal variability is affecting the predictability of ENSO, and I will be giving 2 examples in the 2 next slides on this effect. First of all, here I'm showing the forecast made with the NASA model for the NEO3 index targeting December 2003. The forecast values are as a function of initialization time from January 2003 to December 2003. And the thin lines are showing a forecast of the NEO3 index with a model. And the thick dashed line shows the observed NEO3 index for December 2003. You can see that the ensemble forecast with this model was consistently showing a La Nina event to realize. And until initialization up to June 2003, until suddenly in June, initializations from July 2003 jumped up by more than 1 degree Celsius in the NEO3 index and converged to what happened, what was observed finally in 2003. So yes, we analyzed this sudden jump in the ENSO forecast and find out that intraseasonal activity was very important for this sudden jump, with winds in the Eastern Pacific shielding the surface of the Pacific Ocean from the oncoming Kelvin wave. Another example from the importance of subseasonal variability to ENSO is shown in this slide, where I show you the official CPC Climate Prediction Center and IRI forecast issued on 6 September 2012, which was calling for a El Niño watch. And we all know that ENSO forecasts from September to December have a very, very significant scale, very high scale, exceeding 0.9. So what happens is that 2 months later, in 8 November 2012, the ENSO alert system was downgraded to not active. Meanwhile, if we check the status of the MGO during this August-September period where the first forecast was issued, we can see that during August, a very significant, very strong MGO event was entering the Indian Ocean, but started to collapsing in the Eastern Indian Ocean towards the first part of September, just before this forecast was issued, just to come back roaring in the Eastern Indian Ocean, the maritime continent, and then meandering in the Western Pacific. So basically, that's another example that there is a lot of need for MGO to enter research. So the DYNAMO campaign. I think we all know that the subseasonal forecast is very important for many reasons, and better observations can help to better understand the physics of subseasonal variability, and of course face the forecasting challenges. And therefore, towards this direction, DYNAMO campaign was designed and funded by all the relevant agencies. And what was DYNAMO? Basically, it was a component of an international campaign called CINDI, and started in November 2011, and ended. The official end was the 31st of March 2012. And during this campaign, we sent radars, planes, radio zones, and ships in the Indian Ocean, basically in the area of the Maldives, with, for example, the French Falcon being located on the Gun Islands, the NOAA's P3 in Diego Garcia. The US Revel was located in this area here on the equator, and the Japanese Mirai just south to the equator. Also, there was a deployment of moorings shown, the location of which are shown with the yellow dots here. So DYNAMO was a lucky campaign, and if it had happened 1 year before, then nothing would have been observed. The Indian Ocean was really quiet. So this is a review of what happened during DYNAMO, a review seeing through the RMM index. And in the left-hand side panel, I'm showing you this RMM index from October to December 2011. You can see the blue line shows the values of the RMM index in October. And as the campaign was starting in the 1st October, a strong MGO event was traversing Africa, entering the Indian Ocean, obtaining very significant values, over 2 standard deviations, and then plunging, but instead of collapsing, it continued, crossed the maritime continent in November, made the round of the Earth, and then came back in the Indian Ocean with roaring, with again amplitudes exceeding 1, 2 standard deviations. And then the MGO continued traversed the maritime continent, started meandering in the Western Pacific, and the right-hand side shows the evolution from January 1st to March 31st. So it was meandering in the Western Pacific until it started growing again in February, as you can see, with values exceeding 3 standard deviation, getting into Africa and entering the Indian Ocean, traversing the maritime continent, and again going to the Western Pacific. So from this point of view for the RMM index, there was a multitude of MGO events that were observed. However, it wasn't only MGO that was observed during DYNAMO. This is the composition in tropical modes, atmospheric modes, equatorial modes, Kelvin waves, Rossby waves, and MGO during DYNAMO of the OLR field, average from 7 south to 7 north. You can see with black lines the MGO events that I was just describing, with a huge event happening in February, March 2012. But also you can see a plethora of Kelvin waves shown in green, propagating from west to east as faster than the MGO. But also a lot of Rossby waves occurred, propagating from the east to the west, shown here in magenta colors. So DYNAMO observed most of the modes that represent the subtropical variability in the tropics. Now, DYNAMO not only observed this multitude of events, but also events of with different qualitative characteristics, as I show here. The right-hand side panel shows a Hofmöller of outwave long-wave radiation, average from H south to the equator, as a function of time and longitude, where you can see very clearly the MGO events that I was just describing, with the last one, the very strong last one, that occurred in February, March 2012. And we can compare this evolution of the OLR with the evolution of sea surface temperature on the left-hand side panel. You can see that for the first event, there was basically no subseasonal variations of the SST. For the second event, there were positive anomalies of SST preceding enhanced MGO convection, and negative anomalies following SST anomalies following this enhanced convection. But this behavior was just confined in the Indian Ocean. For the last very strong event, we can see that strong and persistent SST anomalies were preceding this strong organized convective event, and then these SST anomalies started propagating into the Eastern Indian Ocean and to the Western Pacific, and were followed by negative anomalies, which in their part were following the organized convection. So basically, we could separate three types of events here. The first one, as we can describe as uncoupled. The second one as weakly coupled, and the third one as strongly coupled. Typical observations during DYNAMO are shown in this figure, where I show the relative humidity observed by radiosones as a function of time and altitude over the island of Gan, over the Revel, over Diego Garcia, and over the Mirai. Over Gan, you can see very clearly the several MGO events that I was just describing appearing in the relative humidity field, and it's very, very clear that humidification of the lower troposphere was preceding humidification in higher and higher levels, as suggested by many theories. So using this data, we can already start doing some theoretical analysis. And this is, I think, a quite interesting graph, which presents lag correlations between the negative RMM2 index, which describes the MGO entering in the Indian Ocean, versus DYNAMO observations from at the Guyana Island of relative humidity shown with colors, and of zonal wind shown with the thick black lines. Here we can see that as the MGO was entering the Indian Ocean, there was easterlies appearing over Gan, and these easterlies were preceding humidification of the lower tropospheric levels, humidification which shown here with this vertical sloping bar was eventually reaching higher and higher levels until this humidity and MGO connection became non-correlated as westerlies appeared in the lower troposphere, reaching down to the surface through the atmospheric boundary layer. This is what we could expect from the moisture recharge processes as described in the literature. Now, what we did for DYNAMO at N7 University of Maryland was to use the relevant NCEP models, the GFS, which is the highest resolution running at NCEP, the GFS, which is the ensemble model, and the CFS, which is the climate forecast system, which is a coupled ocean atmospheric model. And we use this forecast to tailor products specific to the requests of DYNAMO PIs on the field. These products were fitting first weekly the special weekly CPC GTH Global Tropical Hazards Outlook product that is produced by human forecasters, but also 6 hourly, daily, and weekly directly sending products to the Dynamo campaign. We're also doing this project. We also assured that Dynamo observations that were entering the GTS, the Global Telecommunications System, were effectively assimilated by the data simulation systems at NCEP, and then fed to the forecast models. And one third part of this project was to try to understand differences between the model forecasts and the Dynamo observations in order to understand better the physics and of subseasonal variability, and then potentially improve models. So this is a review of the CPC GTH Dynamo Outlook produced by a forecaster team every Wednesday at 8:30 local time, Eastern Coast. And this is the October case. This is an October case for week 1 outlook and week 2 outlook, valid October 19th to 25 for week 1 and 26th to November 1st for week 2, where you can see enhanced, the team was forecasting enhanced probabilities for precipitation over the Western Pacific, Western Indian Ocean and the Central Indian Ocean, propagating to the Eastern Indian Ocean and the Maritime continent. And it's exactly the time of the first, this was exactly the time of the first MGO event forecast observed by Dynamo. So this was a very successful forecast. And summarizing all the forecasts that were made during all Wednesday mornings during the Dynamo campaign, here is the review of the height key skill score, the mean values for week 1. You see the average is about 25.2, and for week 2 the average is about 19. And the spatial distribution of this score, where we can see the red values are good values, the blue values are bad values, and you can see that mostly good values, with the exception of Africa and the Maritime continent for both week 1 and week 2. Now, how did the models do? This is the upper panel show forecast of anomalous outgoing long-wave radiation with the GFS, for week 1 in the left-hand side panel, and for week 2 in the right-hand panel. And we confront this with the verification, the observed by satellite fields. You can see that in the verification panels, you can see that large-scale organized convection was present during this time and propagating eastwards, accordingly with a typical MGO hypothesis. Now, how did the model do? As you can see, during week 1, the forecast was sort of okay, with a large-scale convection in the Western Indian Ocean. But for week 2, instead of maintaining this organization, the model collapsed. The model presented very dry conditions over the equator, with enhanced convection only at 1 Rossby radius of deformation from the equator. This happened also in the second, and of course the third, but I won't show the third MGO event. This is the November MGO event, the model forecast for week 1, the verification, where you can see that for week 1 things are kind of okay, but for week 2, instead of even enhancing even more and organizing better this large-scale convection, the model again presented dry conditions, decreased the convection over the equator, with again enhanced convection to the north and south of it. Now, trying to understand reasons for that, I'm showing you again the lag correlations between relative humidity and winds and the negative RMMM. So that show over GAN, that shows what was happening over GAN as the MGO was entering the Indian Ocean. The upper panel is what we found with using Dynamo observations. The central panel shows the GFS physics at 24 hours after initialization of the model, and the lower panel shows exactly the same physics at about 7 days from the initialization of the model. you can see that even at 24 hours after initialization, the GFS presents a less marked vertical propagation of this relative humidity coherence with the MJO mode. And this coherence is completely destroyed after 7 days from initialization, although the dynamics, the winds, the zonal winds, present some strong similarities again, even after 7 days. So what we see from these pictures here is that a very fast decoupling between the dynamics and the thermodynamics in the GFS, and this coupling is suggested by many theories as very important for the evolution of organized convection towards the east. Now, addressing the coupled versus uncoupled forecast during Dynamo, I will remind you again that there were three kind of type of events observed during Dynamo. The first one was what I'm calling uncoupled. The second one was weakly coupled with coherent behavior between SST and convection only in the Indian Ocean. And the third was strongly coupled with coherent behavior between SST and organized convection in the Indian Ocean and in the Western Pacific. So let's see what the coupled forecasting system and the global forecasting system of NCEP did during these three different periods. So these are anomaly correlations between the RMMMs. Continuous lines show the RMMM1, which describe the MJO traversing the maritime continent and entering the Pacific Ocean. The dashed lines are the RMMM2, which describe the MJO, the minus RMMM2 describing the MJO entering the Indian Ocean. And the red lines show the uncoupled NCEP model, and the blue lines show the coupled NCEP model. You can see that for the first event, Dynamo event, both coupled and uncoupled models were basically present the same kind of type of scale. For the second event, which was weakly coupled with this coherent behavior between SST and convection being located in the central Indian Ocean, within the Indian Ocean, you can see that the uncoupled model, RMMM2, which again I remind you describes the MJO entering the Indian Ocean, the scale drops really fast in comparison to the coupled model. And for the third Dynamo event, which was very strongly coupled in both Indian Ocean and Western Pacific, we can see that the uncoupled NCEP model lost significantly faster scale than the coupled model. So I don't have too much time to describe ocean forecast, but I'll try to make it fast. These are forecasts from the moorings from Dynamo, the D1 mooring on the equator, and the D2 mooring at 2 degrees south of the equator for temperature as a function of depth and time, and salinity as a function of depth and time. What I want to show you here is the lower panels, which shows the anomaly correlation scale, the correlation scale for the model temperature forecast as a function of depth, for week 1 in blue lines for the equatorial mooring, and red lines for week 2, and for the south equatorial mooring, again, week 1 in blue and week 2 in red. The good thing is that week 1 and week 2, the SST, the surface temperature forecast was quite good, and the scale was dropping, but not as significantly as it was doing so in the depth of in the bottom of the ocean mixed layer. As you can see, very significant drops from week 1 to week 2, and this drop didn't affect week 1 and week 2 forecast eventually, but there are many questions on their impacts to week 3 and week 4 forecasts. So as a summary and conclusions, NCEP and ESIC provided real-time monitoring and forecast support to the Dynamo campaign. The team of forecasters issued skillful week 1 and week 2 outlooks of specifically tailored products for the Dynamo needs. In the GFS model, we noted a fast decoupling between the dynamics and thermodynamics of the MJO, which, as theory provides, suggests this hampers the eastward propagation of large-scale convection. And there were times when convection and SST were evolving in a coherent way. During this time, the coupled CFS presented a better skill than the uncoupled GFS. Right. The ocean model presents a very fast drop of forecast skill at the base of the mixed layer with possible impacts to the forecast of SST for week 3 and 4, and eventually for the forecast of MJO. Work to follow is systematic investigation of the capacity of the different models to represent the individual modes of subseasonal predictability, i.e. the Kelvin, Rossby, and MJO modes, and research on optimal multimodal consolidation. And then also that the success of the team of forecasters indicates that many improvements can be made in the models. I think that we need to first investigate reasons for the decoupling between thermodynamics and dynamics in the GFS, and also investigate predictability of SST at week 3 and 4, and examine the ocean mixed layer as a source for this kind of type of errors. Last but not least is we need to gather all these findings and transition to operations to enhance the forecast skill of the global tropical hazards and benefits outlook of the Climate Prediction Center. And of course, extend the GTH to week 3 and week 4. And as a final example, I'll show you this operational product from the CPC GTH, where I'm showing outlooks for week 1 and week 2 valid October 17th to October 23rd, 2012, and October 24th to October 30th, 2012. And as I was mentioning, basically these forecasts are resting on subseasonal modes of tropical variability. And you can see that these forecasts were showing enhanced, very enhanced probabilities for tropical cyclone formation, exactly where Sandy developed. So this kind of type of research is not only interesting for academic reasons, but has direct impact to society. And that's all I had for today. Any questions?
Thank you so much. Your talk was really interesting, and I'm looking forward to seeing your improvements on the week 3 and week 4 showings of the tropical hazards. At this time, I think we're going to ask to hold questions to the end, and Hunter's going to explain to you guys how the process for asking questions goes about with this webinar, because the phones are all on mute, is my understanding.
Yeah, because there are so many people on the line, the most efficient way to field questions is to have you type them in the question box, which is part of the control panel that you'll see probably on the right side of your screen. That's kind of in conjunction with the presentation that you're seeing. So throughout the next presentation, and whenever you have a question that comes up as it relates to that presentation or the one you just heard, go ahead and type in your question, who it's for, and your name in the question box, and send that to us, and then we'll be able to ask that question at the end of the presentation.
Okay. Our next speaker up is Simon de Zerk, and he's an assistant professor in the College of Earth, Ocean, and Atmospheric Sciences of Oregon State University. His research interests are in atmosphere-ocean interaction and its influence on the climate, specifically in the tropics. On this project, he has been working in collaboration with Chris Farrell and Alan Brewer at NOAA's Esra Lab in Boulder. Simon, I think we've turned the controls over to you, and take it away. Welcome.
Hey, thanks, Sandy. Yeah, thanks for the opportunity, too. And I want to thank Augustine for a great talk, and very interesting and provocative, and also a good introduction for my talk. They don't have pictures of ships, and it also shows a lot of the backgrounds that I realized I omitted when I saw that great introduction. So I'm going to be talking primarily about the data that we collected aboard the Ravel from the equator at 80.5 degrees east. We're 3 legs where the ship was more or less on station in that location. I'm also doing the same diagnostics on the Toga core data, because from that we get 2 or 3 more MJO events that we can analyze in almost the same level of detail. But I'm not going to show that today because there just isn't time for it. And I'm also I'm interested in the air-sea interaction that we observed in DYNAMO. So I'm using globally compiled reanalysis and satellite analyses of flux products, gridded flux products. And from these products, for example, trop flux is the one I'll show today. I can get 27 years of daily flux estimates. And I'm not going to show the comparison today, but these products agree quite well with the synoptic and interseasonal variability that we observed in DYNAMO. So I'm going to show that heat transfer through the air-sea interface is related to MJO convection. Probably not a big surprise anymore. The question remains, and maybe it depends based on Augustine's talk, maybe I'm thinking maybe it depends on the event, but does the evaporation anomaly, if the coupling is important with the SST, then one would think that the evaporation, which is the main transfer of heat from the ocean to the atmosphere, would be important for the precipitation anomaly, which we would think of as the convective engine or the convective fuel of the MJO. And then I'm going to move on from the DYNAMO observations, and I'm going to composite a whole bunch of MJO events. I get 103 events from a certain criterion, and I'm going to look at the phase of the air-sea interaction response. So what's the phase of the wind stress to the sea surface temperature to the precipitation, for example. And see if they're, because these are global analyses, I'm using now a pointer. I can also, because they're, because I can use the Tropflex global analysis to examine the difference between the DYNAMO location in the Central Indian Ocean and the core location in the Western Pacific. And then with a little bit of motivation that I'll get to, I'm going to compare the MJO versus the air-sea interaction composite for MJO versus Kelvin Waves. So this is a rather busy figure, and it's because I'm working on putting it in a paper where you try and pack as much in as possible. But I hope to be able to walk you through. On the top is the heat budget. So the solar radiation is this blue term, and positive terms warm the ocean. So solar radiation is always warming the ocean, but with some variability. It drops down on these days. I'll talk about that in a second. The biggest cooling term is the latent heat, which is cooling the top of the ocean. And then to some the long wave heat flux, which doesn't change a whole lot, is this red one, and the sensible heat flux is here, but it's very small, so I'm not going to talk about it very much. The net heat flux is this black line, which is simply the sum of all of them. And you can see that some days have a negative net heat flux, and those days are highlighted in green through all the panels. And you can see that all of these variables, I put them together because they are all, to some degree, all coupled to each other in some way. So you can see that on days when the heat flux is negative, there tends to be more rain. You can see these rain events at the end of November and at the end of October. And we just caught the end of a rain event probably on the third leg of DYNAMO in the middle of December. We didn't probably catch the start of that event. So these negative heat fluxes are correlated to convection through the rain. This blue shading here is cloudiness. So actually the blue is clearness. So the cloudy is the white stuff up here. So when it's cloudy, it's raining. And the, oh look, okay, I'll get to that in a second. The wind stress, you can see, is higher. This is the zonal wind stress, but it's very highly correlated to the wind stress magnitude is higher on these days of stronger evaporation or latent heat flux. And that's not a big surprise that the wind stress on the ocean or the wind speed on the ocean is driving stronger evaporation. But it's an interesting story that it goes along with the strong rain events. Now, in terms of, so these convective events are also clearly intraseasonal variation of convection, and the fluxes are also clearly affecting the sea surface temperature, with the sea surface reaching 3 maxima during DYNAMO, although the third one is arguably not very well observed. You can see it starts going up when we observed it, and it's going down after we finish observing it. And there is a maximum in the APL buoy temperature, sea surface temperature record. So you can see the sea surface temperature goes up and down, and when it's going down are these times when the net surface heat flux is cooling the ocean. And that seems to be true for all of the events. Also, probably more related to the convection than the SST directly, that you get these strong cold temperature, cold pool, surges of cold air over the sea surface temperature in the negative flux, in the cooling days where the ocean is cooling. All right, so next I'm going to show, this is a heat budget, I'm sorry, a water budget. There's a lot of theories on the moisture modes for the MJO, so I wanted to, and it turns out that we can observe most of the terms not only with the DYNAMO sounding array, but also with observations simply on soda straw observations, just simply looking up at the column right above the ship. So this is the microwave total water path. So the microwave radiometer retrieves liquid water path and integrated water vapor, and the integrated liquid water path. The liquid water is negligible, but I added it in just for completeness. So it's mostly vapor, and you can see that there are these intraseasonal risings and fallings of the water vapor path, which does suggest a moisture mode or sort of recharge paradigm. But if you look at the individual times when it actually rains the most, there's not a very strong correlation. So in the bottom plot down here, I have computed the column water budget by computing the tendency of the column water from the microwave radiometer. And I've computed everything on daily averages. Admittedly, doing this over a tiny area, like right over the ship, is a fairly noisy thing to do. But we'll just see what it suggests. Let's see. So we observe the evaporation in great detail, and you can see the evaporation of the ocean. While on the previous plot I showed it seemed to vary a lot. On the scale of the amount of variation of the amount of water in the column and the amount of precipitation that's coming out of the sky at any time, from day to day, the evaporation varies only a very small amount. So what this means is that the convergence of water vapor, if the evaporation is more or less the same, it can vary maybe 50% at most. The evaporation is more or less the same over most of the ocean, then what the MJO must do is to converge that moisture over a fairly large area in order to precipitate in the magnitudes that are observed. So these lines are the precipitation, so they're taking water out of the column. And interestingly, at the beginning of these strong precipitation events, here and here, the storage is acting in a sense that more water is entering the column right as it starts to precipitate. It doesn't look like that particularly is happening in the days leading up to the convection, although it may be happening to some degree. It looks like convergence is more important at increasing the column water vapor and increasing the precipitation. So that's from those two events. Okay, I've shown this. I've showed this already, so I'm going to. I think I've explained all the panels, but Augustine mentioned the RMN, and I'm going to talk about large scale. I'm going to go into averaging events beyond the ship observations now. So I wanted to see how representative this time period and this spot is at 80.5 degrees east on the equator is for intraseasonal variability. So in the thin lines, I've just plotted the daily OLR and daily sea surface temperature. OLR being the sort of canonical way to tell when you have intraseasonal convective anomalies, intraseasonal oscillations. And then in the thick blue line, I've integrated, or I've low-pass filtered this with a 10 to 100 day filter. So it's a wide filter, but it's to capture the intraseasonal part of this variability. So that tracks fairly well. And but if you look at if I do a principal component analysis on the global, the blue and lines are both local to Ravel location in Dynamo. If I do an analysis of the global patterns with the principal components of OLR, or if I use the RMMs, which essentially does the same thing, only it uses more variables besides OLR, especially zonal winds, then I start losing amplitude of the OLR, the intraseasonal signal that was observed right at the ship. And the effect is even more dramatic in sea surface temperature. You can see that only the RMMs explain only, the local projection of the RMMs explains only 20% of the, actually only 20% of the OLR too, of the total variance of sea surface temperature or OLR during the dynamo period. So the global indices are the most efficient representations for global patterns, and they're definitely important for doing subseasonal forecasts, but they're not necessarily exactly what we see when we go out and do a field experiment in one spot. Okay, so I'm going to start with the compositing using the trop flux. So I'm going to use the OLR, the intraseasonal variations of OLR, which are pictured on the left, and I think I've intraseasonally filtered sensible heat flux and latent heat flux on the center and the right panels. And so this is a Hofmahler plot, and my Hofmahler plots almost always go the opposite way as NCEP's ones and John Gottschalk's ones, and the time goes from bottom to top. So the time is going to go this way. And so the idea is that I can, based on the intraseasonal variability in the OLR, these intraseasonal variations here. Sorry, these are, so this is 3 years. So these are intraseasonal variations. I can composite and what I'm going to do is not composite the filtered field, but I'm going to composite the full field of the surface variables. So here's the outgoing long wave radiation and the sea surface temperature. So the outgoing long wave radiation is composited on the phase of the outgoing long wave radiation. So you get what you expect to get. That's what it's almost a tautology to do this, but it's just a check. So you can see that there's high convective clouds during the OLR intraseasonal. During low OLR, there's low OLR that propagates from the Indian Ocean, this is longitude here, over into the Western Pacific, and that's associated with high convective clouds, and then there's high OLR in between, and it's clear in between. And then in each plot, I'm going to plot with black contours the low OLR anomaly, so that as we get to different fields, you can see how they stack up against the outgoing long wave radiation. And so here's the sea surface temperature, and you can see that there's cool anomalies on average with very small magnitude on average. So this may have to do with some events being more coupled than others. And they tend to be more or less in quadrature with the OLR anomaly. So that's consistent with the picture that there's, well, let me show the rest of the fluxes. Okay, so here's the outgoing long-wave radiation and the sea surface temperature. It turns out that the SST is noisy enough that if I filter it, if I just take the derivative of it, it's even more noisy, but the picture shows very clearly to me by eye. I can see that the sea surface temperature is cooling down under the high convective clouds and the low OLR anomalies. At this time, there's also strong net surface heat flux anomalies. When I plotted this, I wasn't sure whether I would find net surface heat flux anomalies cooling the ocean. Sorry. Yeah, so the blue lines are cooling the ocean. Negative cools the ocean in these plots. I'm not sure if I would find these synchronous with the convection or behind the convection, because there is a suggestion from Toga Core that there's strong winds behind the convective event, and those strong winds were cooling the sea surface temperature off further. Now that sea surface temp, let's see, yeah. So we found that on the average of these 103 events, that the convective anomalies represented by the OLR is synchronous with the surface heat flux anomalies. And then these are all the terms that go into the net surface heat flux. You can see that the solar flux is, from the sunlight, is strongly modulated by cloud forcing. During the convection, there's stronger clouds, and that reduces the heat flux. And that's a large term, the largest term, actually. So that is part of the reason that it's synchronized. But that's somewhat compensated by long-wave heat fluxes. When you take all these various terms and their amplitudes and their various phase shifts from each other, you get back this result, where the convective part is cooling the ocean most strongly on the whole. Okay, so I'm going to motivate the next part, which I'm going to talk about Kelvin waves, by noticing this double structure part, this double negative heat flux, double convective maxima in the MJO2, which was in late November, and separated by a couple of days here, where the heat flux is not particularly, it is not negative, and it's not particularly anomalous. And so these two events actually resemble quite closely convectively coupled Kelvin waves, such as have been composited by Straub and Coladas, and here reproduced from Coladas et al. 2009 composites from Majuro. These are on the right, you see the time series of soundings over the Rebel from DYNAMO, and on the left you see the composites from Majuro, and the two Kelvin waves are indicated here. So this is the temperature on the top, and you can see the lag between the warm anomaly in the upper troposphere and the specific humidity anomaly in the middle troposphere, and the wind anomalies which follow that and then tilt back towards the west are reproduced very well. It's almost textbook that these look just in vertical structure, temporal vertical structure, they look just like convectively coupled Kelvin waves, or that which has been observed and called convectively coupled Kelvin waves before. Also, if you look at Hofmüller's, let's see, this is longitude along the left side, and time is running from left to right. So there's these, you can see this is the trim precipitation. You can see the maximum here. You can ignore the green lines a little and let your, well, it's hard to ignore them. They're there. You can see there's a precipitation anomaly here, which sort of peters out, around the maritime continent, and another precipitation maximum starts in mid to late November, and they both are incidents on the Revel a couple days apart from each other. So it explains this double precipitation maximum. But they also propagate at the convectively coupled Kelvin wave speed that we would expect. I think that's about 8 to 9 meters per second. So the next, one of the things I did is take these time series of OLR anomalies. So this is the full OLR anomaly on the left, and I1, I2, and I3 stand for Indian 1, Indian Ocean 2, Indian Ocean 3. Those are the MJO1, MJO2, and MJO3. And I spectrally filtered them to capture eastward propagating Kelvin waves, which is in the central panel, and westward propagating Rossby waves. And I'm going to talk about the eastern propagating Kelvin waves only. And so I'm going to compare the Kelvin waves with the MJO, because what we were calling, when we were on the ship, it was quite dramatic to get these bursts of rain and wind stress, and we were calling them MJOs. Some of us were calling them MJOs, and even though we knew that the MJO was this intra-seasonal thing, I wondered if there's a difference in there's clearly a difference in their scale. Is there a difference in their mechanics and in their air-sea interaction? So, and it turns out that there is. So I composited the OLR and the trim microwave rain, which has no, does not use any infrared in it. Because if it uses any infrared, then it's going to, I'm afraid it may be correlated to the OLR due to that. So this is just microwave only rain. And you can see that the rain, so here's the OLR, and I just composited on the phase of the OLR. So this is phase, and obviously the Kelvin waves are much faster than intraseasonal MJO waves. But so the rain is definitely leading the OLR and the Kelvin waves, while in the MJO it is only maybe slightly leading. And this could be due to the difference between the time axis. The rain may occur and then be followed by large spreading cirrus azoles, which are really strongly affecting the outgoing long-wave radiation. And this could be a separation of a couple of days, while a separation between the rain and the convection in the intraseasonal oscillation is, a separation of a day or two is almost nothing compared to the long time scale of the intraseasonal oscillation. But the dynamics of the Kelvin waves in the MJO are also different in terms of the phasing of the wind stress. Actually, the wind stress seems to be phased more or less the same to the rain, but quite differently to the OLR. And I would say probably it's the same story for the latent heat flux. Well, the latent heat flux is largely dominated by the effect of the wind, which varies much more than the air-sea temperature difference does. So the important point here is the OLR relationship to the rain changes as for the different types of waves. So if you're going to use OLR universally to composite, you may end up with different results that you have to scratch your head to explain. So the last point is that I'm going to make follows on from the wind stress, and you can see that while the wind stress propagates across the Indian Ocean, the maritime continent, and into the West Pacific, and continues on, perhaps at a different speed, maybe at a dry Kelvin wave propagation speed in the Pacific Ocean. The wind speed, or the friction velocity, changes phase in the central Pacific, I guess, near the date line, but actually at about 160 or 170 degrees east. And this is because the mean zonal wind stress changes sign. So we have westerlies, and the mean westerlies may be occurring largely in bursts, but we have these mean westerlies in the Indian Ocean, and then there's trade winds in the central and eastern Pacific Ocean. So that means that the zonal wind anomalies that are dynamically driven by intraseasonal oscillations, dynamically coupled to the intraseasonal oscillations, are encountering different mean wind speeds, and so they have a different effect on the wind speed on the surface. Sorry, they're encountering different vector mean winds, so they have a different effect on the wind speed at the surface, and so that also affects the distribution of latent heat flux. So the phase relation of the wind speed and the latent heat flux changes as we move across the different oceans. So to summarize, a typical MJO convective event cools the ocean with a net heat flux of about 40 watts per meter squared. I think that was actually considerably higher in Dynamo. So stronger events were observed in Dynamo, and also there were stronger events observed in Toga Core. There's a uniform phase of the surface response to convection from the central Indian to the West Pacific Ocean. So those Hofmüller plot composites I showed, the surface variables have the same response over the whole Indo-Pacific warm pool. They didn't vary. So there's not a big difference. Seems like there's not a big difference between the core location and the dynamo location. The two wind bursts in MJO2 in November have moisture and wind vertical structure and propagation like Kelvin waves, and the surface fluxes in Kelvin waves are phased differently, at least to OLR, than intraseasonal oscillations. So I suggest considering using precipitation, if it's available, to composite, find those differences in phases. And from the water budget analysis we did over the ship, precipitation is not explained by local evaporation, I think that's obvious, or the column water storage. And so it really requires anomalous horizontal moisture flux convergence to get the large precipitation during these intraseasonal events that we observe. Okay, thank you very much.
Great, Simon. Thanks a lot. I'm going to have Hunter read. We've gotten a couple of questions on both the talks, so if you guys are capable of staying on the phone for a little bit longer, I know we've gone a little bit over time, but Hunter has a couple of questions he'll read out.
All right. The first one is from Qidong Zhang, and the question is to both of you: how should dynamo observations feed to GFS or CFS improvements?
Okay, can I reply first?
Yeah, I think
yes, please.
It's to you and John Gottschalk.
Oh,
actually.
I'm sorry. Yeah.
Oh.
The first one.
So, yeah, please answer.
Well, I mean, you know, as I was showing, there is a very apparent decoupling from the dynamics and the thermodynamics in the GFS when compared to what we see in Dynamo. And also, I haven't shown here, but the Dynamo radiosondes from at least Gan Island showed that the mean state of the upper troposphere during Dynamo is much drier than what we are seeing with the GFS, which means that, and as I was showing, there is this vertical gradual humidification of upper and upper tropospheric layers. So having a very humid upper tropospheric 200 layer in the GFS can really decorrelate MJO from the thermodynamics. So the data from DYNAMO are can really help us find out which processes are the most important.
All right, thank you. We'll go with one other question, also from Shidong Zhang, and then there was also a comment that we'll send later on since we're pressed for time. But the last question will be to Simon. Tau buoy data has shown about equal amplitude of solar and latent heat fluxes associated with the MJO. Your latent heat flux is much smaller than solar. Could you explain that?
Can I explain it? I suppose, I mean, that's an explanation right there. They're different. Yes. I don't think that they're much smaller. I think that the latent heat flux variations, what I should do, put them up. The latent heat flux variations are a bit smaller on average than the solar variation. I think that these observations are correct, and I believe I think these ones are probably better than the tau ones, but I also believe the tau ones, and there's just a difference. Is this a question from the same place?
Yes, from the same person.
So they're both from Shidong.
Both from Shidong.
So was the tau observation right next to this? I mean, you can see there's a lot of variability in this, and this is maybe not a long enough record to say what the standard deviation is with a very high degree of confidence. I think it's just sampling differences rather than, yes, okay, that's the answer. I think it's sampling differences. They're observing different things. Sorry.
Yeah, that sounds good. So I think at this point we'll wrap it up. We're a little bit over time. We want to thank you for joining us today for the first set of presentations in our series. Thank you guys, the presenters, for putting together and sharing your time putting together presentations and all the rest. And thanks to Amrit, who has been working the technology side of this and going through our inaugural kickoff here. So please join us again in 4 weeks. Our next webinar series is on Wednesday, June 25th at 2 p.m. And it is going to be Tim Bates at PMEL. He'll be talking about shipboard measurements of aerosol, chemical, physical, and optical and cloud nucleating properties from the campaign. And the second presenter in that series is going to be Shui Chen from the University of Miami, and she'll discuss her work on the convective structure of environmental conditions in MJO initiation over the Indian Ocean. So thank you all for joining us today. If you guys have any specific questions or thoughts, please email me at sandy.lucas@noaa.gov or Hunter Jones at noaa.gov. And we appreciate you guys taking your time today. Thank you very much.
Thank you, Sandy.